Good morning, students. In continuation to the linear measurements, in this session, let us discuss about the angular measurements. So, in the angular measurements, also important measurement in the metrology, it involves the measurement of angle of taper and angle between the surfaces. So, there are two measurements instruments are used. One is the angle gauge, which corresponds to the slip gauge, that is considered as a N standard, and another is the line standard. So in the line standard, we make use of the scale which calibrated with the angular markings. So it considers a line standard. So for angular measurement, no absolute standard is required. So it's the main difference between the linear measurement and the angular measurement. There are some metrological instruments are used for measuring the angles: sine bar, bevel protector, vernier bevel protector, autocollimator, angle decker. So these are some devices commonly used in the angular measurements. Now let us discuss about the autocollimator, how to measure the angle. It is basically it consists of two elements. One is the telescope with eyepiece and collimator. So the two things are combined in one instrument. So it involves measuring the angles without any physical contact of the object. So here it makes use of the optical system, that is the light source and the collimating lens and reflector. So these are some optical systems combined with the telescope. Now let us know the principle of the autocollimation. Now look at the diagram. Here, one is the point source, that is the source of light. From the source of light coming to the collimating lens. As you know, the collimating lens is used here to make the light beams parallel. So after incident on the collimating lens, just convert all the incident rays to become parallel beams. Now all the parallel light beams incident on the plane reflector. Here the plane reflector is just 90 degrees to the axis of the collimating lens, as you see in the diagram. Now the point source is normally located at the focal length of the collimating lens. Now, from the light source, the light beam incident on the falls on the collimating lens, and the lens provide the parallel beams to incident on the plane reflector, which is right angle to the axis of the collimating lens. Here, all the light beams get reflected back to the same light source, because the plane reflector is exactly 90 degrees to the axis of the collimating lens. Now, let us assume the reflector is tilted over the small angle, as you see in the diagram, theta. Now, let us assume the reflector is reflected through the angle theta. Here, as usual, the light rays are reflected by the angle 2 theta. Here, again, it falls on the collimating lens. Again, the image will fall on the O dash instead of O, which is X distance apart. So previously we get the image at the same light source. That is, the image again falls on the light source. But here, due to the deflection of the reflected theta, the light rays get deflected by the angle 2 theta, and image falls O dash at O dash, which is x distance apart from O. Okay. Now, from the triangle O dash O, we measure tan 2 theta equal to x by f. Again, x equal to tan 2 theta f. Okay. This is the formula. So from which we can measure the distance. By the formula, we can determine the distance x. So as tan theta is very, very small, we can rewrite x equal to theta into f. Okay. Now, some important points to be noted in the autocollimator is the distance between the lens and the reflector has no effect on the distance calculation x. So the distance between the collimating lens and the reflector has no effect on the distance calculation x. Second, for high sensitivity, that is the large value of x for small deflection of the theta. So longer focal length is required. So longer focal length is it. Okay. Now, if although the distance between the lens and the reflector has no effect on calculating the x value, but if the reflector is too far away from the lens, the light rays will be missed to fall on the collimating lens. There is a chance. So a minimum distance between the lens and the reflector is maintained to capture all the reflected beams and to get the image. So this is the principle of the autocollimation. Now let us move into the next instrument. Sine bar. So the sine bar is another precision measuring instrument for angles. So it is a combination of the wonderful advantages. It is a combination of linear measurement and angular measurements, because the sine bar is also makes use of the blockages. So it also involves the linear measurement also. Here it is a very long steel bar, not pure steel, but the alloy of steel. So the chromium also added to the alloying elements for the corrosion resistance. So in the long bar is provided with the rollers, 2 rollers at both ends. So the working surface of the rollers are finished to the 0.2 micrometer RA value. And there's a lengthy bar and the rollers. Apart from that, there are some leaf holes are provided. So the leaf holes are provided only for 2 purposes: one for easy handling and to reduce the weight of the bar. Now let us consider the working of the sine bar to determine the angle of a surface. Now the sine bar is kept over the surface plate. So next, over the surface of the sine bar, the workpiece for which the angle to be measured is kept on the upper surface of the sine bar. But the condition is the taper surface for which an angle to be measured should face outwards, that is upwards. So over the sine bar, the workpiece is placed, but the condition is the tapered surface on the workpiece should face upwards. Here, the one end of the roller is just incident on or touching the surface plate. Then the roller near the tapered surface is lifted from the surface plate, and from the gap, the suitable combination of the blockages are stacked one over other, so that the tapered surface will become parallel to the surface plate, up to which the slip gauges are stacked by trial and error method. So If the slip gauges are kept in a correct manner, the tapered surface is just made exactly parallel to the surface plate. So the parallelism can be checked by moving the plunger of the dial gauge near the tapered surface and along the entire length of the tapered surface. If there is no deflection, now we can conclude the tapered surface is made exactly parallel to the surface plate. If not, the suitable slip gauges are again stacked so that the taper surface is made parallel. Now, in the calculation of the taper angle, this angle is based on the trigonometry. Now, as you know from the diagram, it forms a right angle triangle. So here the two rollers are exactly at a particular distance apart. That is, the distance between the center of the two rollers are L. We already know. Then the height of the one roller from the surface plate is calculated by combining all the values of the block gauges together. So we can add up all the value of the slip gauges. Now we can find the H. It is H. Now only unknown parameter is theta. Now from the triangle, right angle triangle, we can easily calculate the theta value. Now the sine theta we can take. So in the sine theta equal to H by L from the trigonometry. So from that we can easily determine the theta value. Okay. Here for demonstration, the requirements are the rollers at the bottom should be of equal diameter and two geometrical cylinders, and distance between the two roller axes must be precise and known, and the axis of the two rollers must be parallel to each other exactly. Now the upper surface of the beam must be flat and parallel with the roller axis and the equidistance from each. So these are the necessary requirements to be filled by the sign bar. Then only we can determine the angle without much error. So this is the simple working principle of the sign bar. So the sign center also have the same working principle, because the sign center can be used for calculating the taper angle in the cylindrical workpiece. The cylindrical workpiece cannot be used only with the sign bar. So in the sign center also a sign bar. Over the surface, two centers are provided for holding the circular workpieces. The principle of the measurement is same to the sign bar. Only difference is two centers are attached to the upper surface of the sign bar. The two centers are used to hold the cylindrical workpieces together. The working is similar to the sign bar.